Hello and namaste. My name is Brandon, and welcome to the next video in my series on basic time series. In this video, we will learn about weighted moving averages, taking a very visual approach. So, if you like this video, please like, comment, and subscribe. Let's get started. So first, a few conceptual ideas. Now, in the previous video, we learned about simple moving averages. And the thing is that a simple moving average is a weighted moving average, where each weight is the same. It's spread out evenly across the time window. So in that prior video, we had a 3-period moving average. Therefore, the weight for each value was 1/3, 1/3, and 1/3. Now, all weights must sum to 1 for both the simple moving average and the weighted moving average, the topic in this video. The weighted moving average emphasizes certain past values by weighting them differently. Now, almost always, that means placing decreasing weights backward in time through the time window. But that is not a rule. There is no rule that says that the largest weight has to come closest to our forecast and then smaller back in time. It is completely okay to have the highest weight, say 3 or 4 periods back. For example, if we're looking at some sort of seasonal time series, we could weight the same season back in time even though that is not closest to our current value. So I hope that makes sense. Now, weight values are often trial and error, but linear optimization, for example, solver, can be used to choose the optimal weights that minimize the forecast error when the time series is stationary. Now, notice I put a star there for a couple of reasons. It is important that the time series is made or is naturally stationary. The data we're going to use in this video is a perfect example of why that is. So the data in this example has a very strong trend. And what happens is that if we use, say, solver to optimize the weights, the naive forecast will win out and it will make the weights 0, 0, 1, putting all the weight in the most recent time series because of the trend. So you have to be very careful when doing some sort of optimization. However, if the time series is very stationary, then you can optimize the weights to see if there's a certain mix of numbers that minimize the error. So weighting the time window. In that example in the previous video for the simple moving average, we had a time window that goes along with time, and then we weighted each prior value the same. So one period back was 1/3, the period before that was weighted 1/3, and the period before that was weighted 1/3. And then we summed up all of those, that became our forecast. In the weighted moving average, it's a bit different. So we're going to assume that we weight them over time in increasing weights. So the highest weight is the most recent. So we might have a weight of 0.15, a weight of 0.35, and then a weight of 0.5. Notice a few things here. The sum of the weights is 100 over 100, therefore the sum is 1. And the 15, 35, 50 are weights that I just picked arbitrarily. Again, you would have to look at your data or try different values to see what works best when doing an actual forecast. As I mentioned, the naive forecast is a special case of the weighted moving average. So here are our weightings from the previous slide, and the naive looks like this. We just put all the weight into the most recent value. So it is a special case of a weighted moving average. These are all related. So the naive forecast, the simple moving average, and the weighted moving average are all obviously related. They're just special cases kind of each other, depending on which one you see as the parent forecast. So when we learned about the naive forecast, you were actually doing a weighted moving average. You just didn't necessarily realize it. So here's the data we've been using. This is the GDP per capita for the country of Nigeria from the year 2000 up to the year 2020. And then we graph it. It looks like this. So you can see there's a very strong upward trend from the year 2000 all the way up to the year 2014, 2015, and then it declines slightly or kind of levels out. So let's create a 3-period, in this case year, weighted moving average with the weights of 0.15, 0.35, and 0.50. So we begin the process by using the first 3 actual values, which in this case is the year 2000, 2001, and 2002, and then we apply our weights to each of those values. So 0.15 times 1451, 0.35 times 1499, and 0.50 times 1686. Then we just do a sum product basically, multiply those, add them together, and then that becomes the forecast for time period number 4. So when we do that math, we come up with 1,585. That's our forecast for the year 2003. We continue that process down to the next year. Then we shift our time window. So now it's 0.15 times 1499, 0.35 times 1686, and 0.50 times 1764. Do that math, and we have a forecast of 1,697 for 2004. You kind of see how this works. And then we just kind of keep going. So you see now how this process gets started. It's pretty simple, and we just continue down the time series. But first, a warning about software. A generic moving average and a moving average for a time series forecast value are different. For example, some software programs want to put the 3-period moving average and weighted moving average at time period 3 and not time period 4. So it might do something like this. There are reasons for that I explained in the prior video. So if you want to, please check that out. But we want the time period forecast to be in the 4th slot. So it should look something like this. So for forecasting purposes, it must go into time period 4 because time period 3 doesn't make sense in this case because it hasn't happened yet. We actually have to use the 3rd time period there to make our forecast for the 4th time period. So we continue this process on down the time series, and you can see at each step, we're just shifting our time window down 1 time period, but we continue to apply the correct weights. That's why I shaded each cell a bit differently to show that we're weighting each one of those differently. And we get down, and our final forecast here is $2,451. That is for the year 2021. And that is just a weighted moving average of 2018, 2019, and 2020. So it looks like this on the graph. We can see there under the pink dot over on the right, it falls right there a bit above the end of the green actual line. Now, why is that? Well, remember that the weighted moving average here is 50% 2020. It is 35% 2019 and 15% 2018. Now, 2018 and 2019 were higher than 2020. Therefore, the forecast is pulled up slightly from where it ended. And that's completely okay. But when we put it on the line here, we can see where it falls relative to the end of the data. So here are our forecasts that we did in the prior slides. And then we find the forecast error by subtracting the actual minus the forecast. So in the year 2003, we take 1764 minus 1585, and we get a forecast error of 179. And we go ahead and do that down the entire column. Notice that the forecast errors up to 2015 are positive, and the forecast errors from 2016 onward are negative. And we'll talk about why that is here in a second. So as you can see, the forecast errors for the 3-period weighted moving average model are quite large. Now, why is that? Remember, I said this time series has a very strong upward trend. So in doing moving averages, anything with a strong trend like that, the moving average, whether it's simple moving average or weighted for that matter, has significant lag behind it, and it can't keep up with that trend. That's why in this case, we will see that the naive forecast might end up being the best. So in this case, the most recent observation is very important because of the upward trend. So always know your errors. Forecast errors create a new derivative time series that can be a treasure trove of information for you, the analyst. By looking at just the forecast errors, you should be able to reverse engineer how the underlying time series looks. In fact, many forecasting techniques do this very thing under the hood. So patterns in the errors can reveal trend, seasonality, some inflection points in the series, and so on. And examining forecast errors can help in the selection and interpretation of other forecasting techniques. So seeing the errors for one technique might tell you that a different technique would be better. Here are the naive forecast errors we did in the prior playlist. It's just a basic naive forecast where we use the prior period's actual value for the forecast value for the future period. In this case, the pattern holds true also. The actual values on the left are above the forecast values, and the actual values are below the forecast values over here on the right. Now, the next couple of slides I've set up to morph into the other forecasts. So as I morph from forecast error to forecast error for different techniques, make sure to watch the screen. Here's the naive forecast, and here is the moving average forecast, the simple moving average. Now, what did you notice? The errors increased quite a bit. The bars got a lot taller on the left and a lot taller upside down on the right. And the pattern holds true here also. The actual values are above the forecast values on the left, and the actual values are below the forecast values over on the right. Now let's morph this again into the 3-period weighted moving average, where we applied our 0.15, 0.35, and 0.50 weights for the 3 periods before. So, what did you see there? Well, the bars on the left went down, and the bars on the right also went down again, upside down. So we can see that when we went from the naive to the simple 3-period moving average, the bars shot up quite a bit. Then we moved back to the 3-period weighted moving average using our weights. The bars came back down a little bit. The errors decreased. Now think to yourself, why is that? So the naive forecast is essentially a 0, 0, 100% weighted moving average. The simple moving average was 1/3, 1/3, 1/3, or 0.33, 0.33, 0.33. This weighted moving average is 0.15, 0.35, and 0.50. So we saw that as we went from naive up to simple moving average, the bars got larger. Then back to weighted moving average, where we emphasized the most recent values, the bars came back down again a little bit. And that tells us a lot about our time series. So in this chart, we are comparing the errors for the naive forecast in orange and the 3-period simple moving average in blue. In that case, the weights are 1/3, 1/3, and 1/3. As you can see, very starkly, the errors for the 3-period simple moving average in blue are much larger. So in this case, it would appear that the naive forecast produces smaller errors. And between the two, it is the best. So in this chart, we have the errors for all 3 methods together. So we can see the naive forecast errors in the orange bars, the 3-period simple moving average error in the blue bars, and the 3-period weighted moving average there in the light green bars. And what do you notice? Almost all across the time series, the naive forecast in the orange has the lowest forecast error for a given time period. The 3-period simple moving average has the highest error for each time period for the most part. And the 3-period weighted moving average, where we weight closer to the current time period that we're forecasting, is sort of in between the two. It's definitely worse than a naive forecast error, but it's definitely better than the 3-period simple moving average forecast error. Here's a chart of the actual data in green and the naive forecast in pink. Notice the gap between the 2 lines. A series of positive naive forecast errors, which are under forecasts, indicates an upward trend in the series. On the flip side, a series of negative naive forecast errors, which are under forecasts, indicate a downward trend in the series. So going back to that original naive forecast, if we see patterns in positive or negative forecast errors, that indicates to us where the trend is going up or down, and by deduction, where the inflection point is. So when the positive forecast errors flip to negative, we can tell under the hood that is where the time series has a top in it or a bend in it, where it goes from up to down. So here are all the forecasts on the same line. So here is the actual data in this green dotted line. Normally we would not dot lines like this, but I did it so you can tell the actual apart from the forecasts. So here's the naive forecast again. This is the same pink line from the previous slide. Now we'll add in the other 2. So here in the blue is the 3-period simple moving average forecast, where the weights were 1/3, 1/3, and 1/3. Now, the next line will be the 3-period weighted moving average. Where do you think it's going to land on this chart? Well, right in the middle. Remember, when we're looking at the error bars, it was better than the simple moving average, but worse than the naive forecast. So therefore, here on this chart, it falls right between the 2. Also notice that the 2 moving average forecast lines are a bit smoother than the naive forecast. The naive forecast line is just the time series shifted over one period, so it has all the bumps of the original time series. The moving average forecasts smooth it out because it is averaging either in a simple way or a weighted way, multiple values over time. Therefore, it tends to smooth out the time series as it goes forward. Now also notice, where do these forecasts converge? So here's that same graph, but we scaled the y-axis so we can see distinctions between the lines a bit better. Again, this is just for learning purposes. We would not do this on an actual time series chart per se. So here's the actual data in the green dotted line. Now we add in the naive forecast in pink, the 3-period simple moving average there in blue, and then the 3-period weighted moving average there in the lighter green, the solid line. So it goes right between the other two because that's what our errors told us it would do. So due to the strong trend, the naive forecast there in the pink continues to be the best. It's better than the simple or the weighted moving average. In fact, if you remember at the beginning, I put an asterisk next to the bullet that said you could use Solver in Excel to optimize the weights for the weighted moving average. In this case, that asterisk was there because if you do that for this time series in Solver, the optimized weights it gives you back are 0, 0, and 1. And that tells you that the naive forecast is the best because the weighting of 0, 0, 1 is the naive forecast. However, if the time series was stationary, then using Solver to optimize the weights might be more productive. Now notice here, where do the forecasts seem to converge? Well, it's right there around 2017. The question is, why? Well, look, that's where the time series flattened out. That's where it went up, peaked for a couple of years, and then slowly came back down. That is a small period in the time series where it was relatively stationary. And that is why, in this case, the 3 forecast methods converged right at that point. Because there, in the years up to it, it was relatively flat. So here is the forecast accuracy matrix chart we have been building over the last couple of playlists. On the left-hand side, we have the forecast methods we have learned about. So the naive forecast, the 3-period simple moving average, and in this video, the 3-period weighted moving average with weights of 0.15, 0.35, and 0.50. Down the columns, we have forecast accuracy measures. So the MAE, the mean absolute error, the RMSE, the root mean square error, MAPE, the mean absolute percentage error, the MAIS, the mean absolute scaled error, and SMAPE, which is symmetric mean absolute percentage error. So what we do is compare each one down the column. So in the MAE column, we see that the naive forecast is the lowest. Therefore, it wins that column. We can see, though, that the weighted moving average there in the blue in that first column is better than the 3-period simple moving average, but definitely not enough to overcome the advantage of the naive forecast. Same thing for the root mean square column. We can see that yes, the 3-period weighted moving average is better than the simple moving average, but definitely not as good as the naive forecast. MAPE, same story. The weighted moving average is better, but not nearly as good as the naive forecast because at 3.59, it is much better than 5.37% and 6.51%. The MAIS column tells the same story. Remember, the MAIS is basically a ratio. It is a ratio of the forecast error of a given method to the forecast errors of the naive forecast. The reason it's 1 for the naive forecast is because we're comparing it against itself. That's why it's 1. Any number over 1 means that that measure is worse than the naive forecast. If it's below 1, it means it's better than the naive forecast. As you can see, this 3-period simple moving average at 1.9 is much worse than the naive forecast. And the 3-period weighted moving average, while lower at 1.61, is still above 1 of the naive forecast. Same thing for SMAPE. The percentages are very similar to what we have for MAPE. I won't read all this below because I've done it in the other videos, but remember, the basic goal here is to minimize forecast error in whatever units we're using, whether that is absolute dollars in the first 2 columns, percentages in the 3rd and 4th column, or in the case of MAIS, it's a bit different because it's either above or below 1, above 1 being worse than naive, and below 1 being better than naive. And just so you know, I did verify all of this in R by writing my own functions. So I printed the metrics out, did all the math, and you can see that when you compare them to what I have in Excel, they're all basically the same. There are slight differences because of some rounding in Excel versus not rounding in R, and then I kind of brought in some rounded values into R. So they're not exactly the same per se, but as you can see, they're pretty close. The only differences are due to rounding. So the mean absolute error is 120.36. Root mean square error is in the 127s, give or take because of rounding. The MAPE is 5.37%. The maze is 1.61, and the SMAPE is 5.52. So mathematically, they're all the same in R as I calculated in Excel. Sweet. So that wraps up this video on weighted moving averages, a visual guide. So hopefully you saw how they were all constructed relative to each other, and how the naive, simple, and weighted are related, and how their errors can be compared to see which one is the best. Not only that, so you know that it's very important, and we'll get to this eventually, that the time series be stationary before you do any forecasting. It has to be detrended and sort of deseasonalized, and then take the noise out, and we can kind of see what's the underlying time series. Then we can apply some of these techniques that require a stationary time series. Otherwise, we have weird things happen, like Solver optimizing the weights for a weighted moving average to be 001, which is odd. And that tells us the strong trend in the time series. So thank you very much for watching. I really appreciate your time, and I look forward to seeing you again in the next video. Take care, keep learning, and bye-bye.